3 pi over 2. That's where cosine 0. So we get what? We get sine of 3 pi over 2 minus the sine of pi. Sine of pi is 0. Sine of 3 pi over 2 is minus 1. So as I was claiming, that area is minus 1. Signed area, of course. All right, let's enough about sine and cosine. Let's find another function to integrate, yeah? See, I'm trying not to erase anything until he gets back. I don't think I'm going to make it, though. Oh. Oh, I think I can erase the top, actually. That's what I'll do. Example 3.
James, I have one question.
Yeah.
Can you come back? Here, when you have like from this to there,
Mm-hmm.
then both those areas like counts, so it gets like 0.
Yes, it is 0. That's what happened. So the first one is 2. 0 to pi is 2. Then pi to 2 pi minus 2. But then when we go from 0 all the way to 2 pi, we add those together, actually. But of course, you could also just calculate it directly, right? Minus cosine of x evaluated from 0 to 2 pi, which would give you minus cosine of 2 pi plus cosine of 0, also known as minus 1 plus 1, 0. I mean, there's more than one way to see that that should be 0. I was trying to illustrate it by breaking it down into its sub-pieces because, like, you know, I made that example earlier in class, so I was trying to return to it. Okay, so try and do something a little bit different. How about this? The integral from, let's say, 2 to the natural log of 3 of e to the x dx. Let's see here. So this is the antiderivative e to the x is e to the x again, yeah? So we get e to the log 3 minus e to the 2. And so what's e to the natural log of 3? It's just 3 again, right? So we get 3 minus e squared. So here's my question for you. E to the x is positive, right? Why did we get a negative answer? I don't know if you can see it or not, but e squared, it's about like 8. 2.7 squared, I don't know, it's 8-ish, something like that, I don't know. It's definitely bigger than 3. That's definitely less than 0. Why is this answer less than 0 if the function we're integrating is positive? How'd that happen? You got me. It's because 2 is greater than the natural log of 3. So the bounds are out of order. It's not actually calculating the area. It's calculating minus the area, which is why we got a negative. Biology? Is that right? Yeah. Yeah. So you do more with like logs in your other courses, yes? No, you just know log of 3. You just had a sense of it? Educated guess, okay. So it wasn't that you knew that the natural log of 3 was smaller than 2?
I was thinking about it.
Oh, okay. But you're right, it is, log of 3 is like, what is the natural log of 3? Well, the natural log of e is 1, you know? And so that's like the natural log of 2.71-ish is 1. So that means that the log of 3 is somewhat close to the number 1. That's how I knew it, but okay. Anyway, let's do another. We haven't done any polynomial ones yet. We should do one of those. Example 4. The integral, let's say, from 0 to 1 of x cubed plus x squared minus the square root of x. So square root of x is the 1/2 power, right? So here we go. We got 1/4 x to the 4th plus 1/3 x to the 3rd power. And check this out. So if we have x to the 1/2 and you integrate it, you get, you know, x to the 3/2 over 3/2 plus a constant, right? But a nicer way to write that is 2/3 x to the 3/2. And then we evaluate, of course, from 0 to 1. I love having bounds that go from 0 to 1 when I'm dealing with the integral of a polynomial, because it makes the evaluation process like really, really easy. Because what happens when you plug 1 into this expression? You get the same, basically all of the, 1 to the 4th is 1, 1 to the 3rd power is 1, 1 to the 3/2 is 1. My bad for calling that a polynomial, actually. By the way, that's not a polynomial, is it? 3/2 power disqualifies it from the polynomial club. But it's still easy to evaluate at 1. We got 1/4 plus 1/3 plus 2/3. Let me erase this comment over here. What about 0? It's nothing, right? And it gives you nothing, because when you plug in 0, you get 0 again. And so we just got to make common denominator of 12th. So I get 3 plus 4 plus 8, 15/12. Is that right? Did I do that right? I'm not sure if I did that right. Oh, 1/3 plus 2/3 is 1. 1 plus 1/4 is 5/4, yeah? Let's be civilized. 5/4. I would just like to take a second to pause and appreciate what we just did. We calculated the area under this monstrous, I don't even know what this thing looks like, you know, whatever it looks like, from 0 to 1. And we figured out that this area under y equals x cubed plus x squared minus the square root of x, that area is 5/4. It's 1.25. We don't even know how to graph it, but we found the area. This is very neat that we can do this. You're like, another? Yes, another. How about the integral from -3 to -2 of dx over x? What is the antiderivative of 1 over x? let's see here. D dx of what function gives us 1 over x? Wasn't it? It was natural log, right? All right, am I right? The derivative of natural log is 1 over x. So I put natural log here, right? And I got to evaluate from -3 to -2. And I get natural log of -3, -2, minus the natural log of -3. And try plugging that in your calculator, see what happens. If I could find my calculator. What do you think is going to happen? Natural log, what'd you get? Natural log of like -2. What happens? Unreal, yeah. Huh. See, here's the thing. If you take the derivative with respect to x of the natural log of the absolute value of x, right? That's d dx of the natural log of the square root of x squared, okay? Which is d dx of 1/2 the natural log of x squared, which is 1/2 times 2x over x squared, which, by the way, is 1 over x, for x not equal to 0. The formula above that is only for x greater than 0. Right? This right here assumes x greater than 0. But I told you guys that we add a constant because we want the most general antiderivative. Well, that's part of the story. The other part of the story, which is more subtle, is sometimes to be most general, we want to put absolute values in our answer to reflect the fact that when it's negative, we need those absolute values. See, so what was missing and what made this incorrect, and I'll correct it in red, the correction is easy. We're supposed to have absolute value of x here because the derivative of natural log of the absolute value is 1 over x. Always true. When x is positive, we can drop the absolute value bars, right? But when it's not, we can't. We need them. And they save the day. See, because that gives us natural log of 2 minus the natural log of 3, right? And there you go. And that answer is negative because the natural log of 2 is not as large as the natural log of 3. Does it make sense for our answer to be negative here? Why? What are we calculating? Let me point out what we're calculating. This is the graph of y equals 1 over x, right? It's a hyperbola, actually, rotated a bit. And so we're calculating the signed area from like -3 to -2, right? This area right here. That area is below the x-axis, so it counts as negative. It makes sense that our answer is negative here. It should be negative because we're calculating the definite integral of a negative function. And the bounds are in their proper order. Okay. So just, I wanted to warn you about this, all right? There was a time in my life when I ignored this and I got really, really confused as an electrical engineer. In this, I think it was when I was in a semester of electrical engineering and I was careless about this at one point and it just ruined my day. I thought I was doing everything right. Why is this answer not making sense? Oh, dummy. Example 6, absolute value. Example 6. So let's integrate from 0 to pi over 4 of dx over x squared plus 1. So to draw you a picture of the graph here, this is this curve it maxes out at 1, and it's got inflection points like here and here for what it's worth. It's kind of a neat function. So we're calculating the area right in here, right? So of course we expect this to be positive. What's the antiderivative of 1 over x squared plus 1? Let me rephrase it. d dx of what function gives us 1 over x squared plus 1? You're on the hunt. Yeah, inverse tangent. Inverse tangent is the one. So that's what we want here. Inverse tangent of pi over 4 minus inverse tangent of 0 by FTC2. By the way, I have not said this, but on every single one of these examples, my calculation is by the fundamental theorem of calculus part 2. My bad for not repeatedly drilling that into you. I should. Inverse tangent of 0 is 0. Inverse tangent of pi over 4 is what? It is 1. This is 1 minus 0. Let's see, what else can we do? How about integral from pi over 6 to pi over 3 of secant squared theta d theta? I still haven't done any examples of FTC1, have I? Don't worry, I'll get to it. Those are easier. What's the indefinite integral of secant squared theta? It is tangent theta, right? The derivative of tangent is secant squared. So we just do tangent pi over 3 minus the tangent of pi over 6. Which is like sine pi over 3 over cosine pi over 3 minus sine pi over 6 over cosine pi over 6, right? So that's like root 3 over 2 divided by 1/2 minus 1/2 divided by root 3 over 2. In other words, it's the square root of 3 minus 1 over the square root of 3. Of course, you could use your calculator, you know. I'm just teaching trigonometry at the moment, so I know things. One more of these, and then we'll flip over to FTC1. Example 8. What if you're integrating from pi over 6 to pi over 3 of tangent squared theta? Now, tangent squared is not something that has an elementary integral. It's not on our list of like basic educated guesses. But it is related to secant squared. How is it related? We've got what? Tangent squared theta plus 1 equals to secant squared theta, right? So I can trade tangent squared for what? I can trade it for secant squared theta minus 1. Yeah. And so this is the integral from pi over 6 to pi over 3, secant squared theta d theta, minus the integral from pi over 6 to pi over 3 d theta. Now, we just calculated the first one in the previous example. We already know that that first integral works out to root 3 minus 1 over root 3. Listen, guys, like a theorem that you should be aware of, you should think about this theorem, is something that's good to know. If you're integrating from a to b of a constant times dx, the answer is just constant times b minus a. We argued this geometrically today in our discussion about the upper and lower bounds for the function. But we could derive it from FTC2 just the same. Anyway, it's true, and that's what you need here. When you're integrating d theta from pi over 6 to pi over 3, the answer is 1 times the difference of the bounds. Pi over 3 minus pi over 6 is pi over 6 again. 2/6 minus 1/6 is 1/6. So that is simply minus pi over 6. There you go. So I will stop there with the FTC2 examples for today. Let us conclude with some FTC1 examples. I said your homework was due Thursday, right? Did you say it was due today or Thursday? I mean, it can be due to Thursday, I think is fine. Well, I think the homework is definitely due this week, like because I made it shorter. So, you know, let's just, for the sake of specificity, say I will take it tomorrow at the start of class. I might have said today at the start of class, but since that time is gone, I'll let it slide. Anyway, getting to the point here. Calculate the derivative with respect to x of the integral from 3 to x of inverse hyperbolic tangent of t squared plus 7 minus 1 over cosine of t dt. Next example, d dx, integral from 7 to x of the sine of x cubed plus 3 plus e to the tangent of 2, oh, that was supposed to be t, sorry, 2t. What does FTC1 say? It's amazingly stupid what it says. It says when you differentiate an integral with a variable bound, and the variable bound matches the derivative just like that, all you do is you take the integrand, whatever it is, and you replace t with x. That's it. Don't make it more complicated. It's just that. So this is inverse hyperbolic tangent of x squared plus 7 minus 1 over the cosine of x. I did not differentiate. I did not integrate. I just plugged x in the place of t. You should be like, really? This is too good to be true. It can't be this simple. It is this simple. It really is. So here we have sine of x cubed plus 3 plus e to the tangent of 2x. Pop. Done. So I will warn you, just for the sake of, I don't want you to get, like, it does get worse, it does get uglier. I'll show you what that is. If you have something like d dx of the integral from, say, you know, x squared to sine of x of cosine of t squared plus, you know, I don't know, inverse cosh of t plus 8. then we can't just plug in x. All right? You can't just plug in x when it's like this. If your bounds are both variable, if they're not just x, the answer in this case, and this is by FTC3, well, you just plug in the bound. Why did I make these so horrible? I'm an idiot. So all I did was I plugged in t equals to sine x, and then you multiply by the derivative of the bound, which in this case is cosine x. And then you subtract cosine of x to the fourth plus cosh inverse of x squared plus 8, and multiply by the derivative of x squared, which is 2x. In other words, what I'm saying is that like ddx of the integral from a of x to b of x of f of t dt, it's f of b of x times db dx minus f of a of x times dA dx. So when the bounds are variable but they're not just x, it gets more complicated. But is the variable is just x and it's in the right place, it's FTC1 is very, very simple. We'll talk more about this. This is what I call FTC3 in a future class, all right? But for now, we're done. Woohoo! Ending early is a good idea.